Everybody. So I did a little snafu the other day when I turned off my. Good morning, Matthew. When I was working with my ScreenFlow, I told it to quit instead of stop, and so it didn't save it. So this weekend on Saturday, I'll go back and redo the first part of what we covered on Wednesday and post that to the YouTube channel. So today, hopefully, I won't have that mistake and we'll be all right. So last time we started talking about alcohols, right? And we know that there are a few ways in which we can make alcohols and ethers, right? We can make alcohols by SN2 reactions. How would we make an alcohol by an SN2 reaction? What would we need to have as the electrophile, and what would we need as the nucleophile? I need an alkyl halide. Would I need water? I could do that technically, but that's not the way I'm thinking about it. So let's say an SN2 reaction. How would I make an alcohol by an SN2 reaction? Would water be a strong enough nucleophile? Oh, it's pretty weak, right? That's with an alkene. But if you have the alkyl halide, what would my nucleophile need to be? Which one? Okay, I need hydroxide, right? I need hydroxide to function as the nucleophile. And that'll work. We know that, what would that work best for? Primary, secondary, tertiary alkyl halides? Primary, right? So because it's an SN2 reaction, we've got to worry about steric hindrance and all that stuff. Okay. If we had a tertiary alkyl halide, could I still make an alcohol? Yeah, but what would my nucleophile be now? It'd be just water, right? So if we took tert-butyl chloride and we mixed it in with water and a little acetone, remember we did that demonstration last semester, and we saw the formation of an alcohol. How would we make ethers by SN2 chemistry? What's the name of that reaction that I want you to know? Yeah, Williamson ether synthesis. That's exactly right. And it's between an alkyl halide, which is typically what type of alkyl halide? Primary, secondary, tertiary. It's primary, that's right. And a nucleophile, which is an alkoxide, and the alkoxide also needs to be primary, right? It can work with secondaries, but it's best with primary alkyl halides and primary alkoxides, okay? So now we need to start talking a little bit about alcohols functioning as bases and nucleophiles. Why can an alcohol also function as a base or a nucleophile? Okay, what about it though? You're right, you've got the OH, but what about the OH makes it a base/nucleophile? pK, maybe. What is on that oxygen atom besides a hydrogen and a carbon? Lone pairs, right? And all bases are electron pair donors, and all nucleophiles are also bases, right? So, or electron pair donors, that's exactly right. So, we're going to talk a little bit about that. So, it turns out that alcohols will react with strong acids. So, if you take an alcohol, in this case we're going to look at a primary alcohol, and you mix it with a strong acid, HA, you are going to protonate that alcohol and get what's known as an oxonium ion, okay? I like to just call them protonated alcohol, okay? Makes it pretty simple. That makes sense because we have a lone pair, or a pair of lone pairs actually, on the oxygen. This kind of looks like what type of reaction is we have the arrows drawn? Nucleophile coming in from the back, leaving group leaving. Looks kind of like an SN2 reaction on an acid, right? And so we see the nucleophile attacking the acid, or the base attacking the acid, and we end up with a protonated oxonium ion, okay? So what, right? Why is the equilibrium lying to the right and not to the left here? What about your reading assignment in that paper that I gave you in the the first day. That's right. This is a weaker acid than our starting acid, right? And so the equilibrium lies to the right. You're going to find that strong acids like HCl, HBr, HI, H2SO4, when you place those in an alcoholic medium, you're going to have the protonated alcohol. The equilibrium will lie to the right if we have this in a 1-to-1 molar concentration, if you will, okay? And so this looks like what? This protonated alcohol. If we just ignore the R part, what does that look like? Water. And it turns out that water's a pretty darn good leaving group, okay? Water's pretty good. And so some nucleophile can come in and do simple SN2 chemistry, displacing water as a leaving group in an SN2 process, and we can make new carbon nucleophile bonds plus water as the leaving group. Okay? What nucleophile will do this, okay, is kind of a special case. You can't use all nucleophiles because nucleophiles are also bases, and bases also like to react with acids, right? So you couldn't throw in a strong base / nucleophile in this reaction because it'll just deprotonate the alcohol. But there are nucleophiles that work very well here. Can anybody tell me what they might be? Bulky? Well, bulky nucleophiles won't do SN2 chemistry though, right? Huh? Okay. DMSO, that'd be a solvent here. Okay, if we have a weak acid, its conjugate base is strong or weak? You're on the right track. That would be a strong base, right? So it's kind of the opposite of that. What do we want? We want nucleophiles who are the conjugate base of strong acids, okay, for this reaction to work. And so it turns out that we can do this with the hydrogen halides. So instead of HA, if we use HX, HCl, HBr, HI, this reaction works pretty good. And so you can take an alcohol and you can convert it to an alkyl halide by simply treating it with hydrochloric acid, hydrobromic acid, or HI. Okay? You can convert them quite easily into the alkyl halides. So the functional group transformation that we're talking about here is how can we take an alcohol to an alkyl halide. There are other reagents that work as well. The phosphorus halides work really well, like PCl3, PBr3. Thionyl chloride is another common reagent for making alkyl halides from alcohols, and we're going to talk about the mechanisms of those today. Okay? If HX works so well, why do we need additional reagents? Can anybody tell me why? Give me an example. If we're thinking about these things as tools in our toolbox, why do I need another screwdriver in my toolbox? Why can't I just get away with one? How come my toolbox has all these wrenches and screwdrivers and different things in it? They work with different types of things, right? And so different substrates. So if we think about it, let's suppose that Carl comes into the lab and he tries to do this. And he finds that that works just fine. Okay, well, that's good for making ethyl bromide, but what if he comes into the lab and he wants to do this? Why won't that work as written? That's right, because we can also add HX across a double bond, right? So we need reagents that won't add to double bonds, and that's what the SOCl2s and the PX3s will do for us. They will help us be more selective in terms of the chemistry that we want to do. And so that's why we frequently need more tools in our toolbox than just the simple ones, okay? So let's look at some examples. Okay? Here's an example where we're taking butyl alcohol. We are either using dry HBr gas or we're using a mixture of sodium bromide and sulfuric acid and refluxing it. What's the product going to be? Predict the product for me. What do you think, Sarah? What's the functional group transformation we're going to do? We're going to take an alcohol and convert it into a what? What alkyl halide here? A bromide. That's exactly right. Is it going to be 1 bromobutane, 2 bromobutane? And why do you say that? It is going to be 1 bromobutane. Why do you say it's going to be that, though? That's where the OH is. And so are we going through a carbocation intermediate or an SN2 reaction? We're going through an SN2 reaction. That's exactly right. We know that because we have a primary alcohol. That primary alcohol is going to become protonated, and then the bromide is going to come in and displace the water. It's an SN2 reaction. What's this business about sodium bromide and sulfuric acid? Is sulfuric acid a stronger acid or a weaker acid than the hydrogen halides? It is a stronger acid. So what do you think is going to happen, Matthew, when I take sodium bromide, which is a salt, and I put it right here in front of Rose and I start dripping in a little concentrated sulfuric acid? What do you think it's going to make? It makes HBr. That's exactly what it does. And so HBr is a gas. It's hard to work with. And so chemists like to work with things that are easier to work with. So sodium bromide is a nice salt that sits on my bench. I don't have to worry about it. Sulfuric acid, well, I got to worry about it a little bit. But it's a liquid. I can handle it pretty easily. So anytime you see sodium bromide and sulfuric acid, think of that as HBr. When you see sodium chloride and H2SO4, think of that as HCl. Okay, we frequently use those as replacements for the pure gases. This next one, propyl alcohol, HCl zinc chloride reflux. What do you think we're going to get? What's the functional group transformation going to be? Alcohol to what? Alkyl chloride. That's right. Where's it going to be? It's going to be primary. That's right. That's exactly what we're going to get. We're going to get propyl chloride. Notice we're not just using HCl. We're using HCl in a mixture of zinc chloride. This is known as Lucas's reagent. Okay? Yeah, Gabby. Reflux means to heat to boiling. Okay? You all will reflux things quite a bit this semester. But if we boil something, it evaporates, right? So you put what's known as a reflux condenser on it so that the gases come up, touch the cool walls, forms a liquid again, and just drips back down into the reaction flask. That's what reflux means. Okay? Why do we need the zinc chloride here? Can anybody tell me? Zinc metal is a reducing agent. That's correct. But do I have zinc metal? No, I've got a zinc salt, right? Is chloride a good nucleophile in this series, or is it the worst nucleophile in the series? In the series. It's the worst, because remember, as we go down a family, the nucleophilicity goes up, right? It turns out that chloride is not a particularly good nucleophile, and so you have to add another Lewis acid, in this case zinc, to make this reaction go quickly, okay? And so you add Lucas's reagent. It makes the primary alcohols get converted into the alkyl chlorides much more efficiently. Will it work without zinc chloride? Yes, you'll just be waiting a really long time, okay? So what do you think the mechanism is here, SN1 or SN2? So if it was SN1, the alcohol would be removed. I'd end up with what carbocation? That's right, so it would rearrange, right? If it were even formed, right? So is that what we see? No, so it's got to be an SN2 reaction. That's exactly right. Now here we're taking tert-butyl alcohol. We're mixing it with concentrated hydrochloric acid at 25 degrees Celsius, which is basically room temperature, right? What do you think the product's going to be? What do you think, Delaney? That's right. We're going to end up with tert-butyl chloride. What do you think the mechanism is going to be here? SN1 or SN2? Okay, if it's SN2, we're going to protonate that alcohol, right? And then the chloride would have to come in from the back side and displace it. Does that seem plausible here? And why not? There's a lot of stuff. It's tertiary, right? Okay, very good. So it's got to be an SN, it's an SN1 reaction. So we're going through a carbocation intermediate. This reaction is actually one of the easiest reactions you could ever do. And in fact, it's so easy we don't want you doing it in the teaching lab. Okay? It's not really challenging at all. We make our tert-butyl chloride in our lab because it's so easy. We buy a bunch of tert-butyl alcohol, which is dirt cheap. You actually pay more to have it shipped to you than it costs. And we go over to the stockroom and we buy some concentrated HCl. We pour 100 milliliters or so of this into a separatory funnel, and we add about 100 milliliters or so of concentrated hydrochloric acid, which is in water, right? Is tert-butyl alcohol soluble in water? Does it meet our rule? Yes. And so it starts off as a homogeneous mixture. And you mix them together and you just shake it up a little bit. And you set it in a stand. And what starts to happen over time? Pardon? We start to see a second layer floating on top. And what's that second layer? Well, you're not going to see, the water is the lower layer. It's the alkyl chloride. That's right, the tert-butyl chloride. Because is it soluble in water? No. That's exactly right. And in about 20 minutes, you see these two layers form. You simply drain off the lower aqueous layer. You collect the top layer. You may wash it again with water to get rid of some of the acid, and voila, you have beautifully clean, 100% yield, essentially, of tert-butyl chloride. It is so easy to do, you cannot mess that reaction up. Okay? Whoops, there we go. Wrong button. Well, let's continue talking a little bit about how we can convert alcohols into alkyl halides. It turns out to be a pretty important reaction. And it turns out that we find that acid promotes this reaction very well. So if we have stronger acids than the hydrogen halides, like sulfuric acid, the reaction goes much quicker. We also notice that carbocation rearrangements are quite common. So if you have secondary alcohols and tertiary alcohols, you will find rearrangements occurring in these reactions. Okay? Only the primary alcohols avoid it because we can't get a primary carbocation very easily, right? So if we take Gabby's favorite alcohol, 3,3-dimethyl-2-butanol, and we mix it with HCl, she does not get a secondary alkyl halide. It's not protonation of this alcohol followed by chloride displacement, right? The alcohol gets protonated, and then what happens? It leaves and gives me a carbocation intermediate, which then rearranges. Very good. And then that carbocation gets trapped by the chloride, which gives us this molecule, right? We find that the reactivity order of the alcohols towards HBr, HCl, and HI follows this trend. Tertiary alcohols react fastest. They react faster than secondary alcohols, which react faster than primary alcohols. But primary alcohols react slower than methyl alcohol or methanol. Can anybody explain that trend to me? What do you think, Carl? Why do you think a tertiary alcohol reacts faster than a secondary and a primary? Let's just worry about that one first. What do you think, Mason?
The carbocations are stable, the tertiary carbocations.
That's right. So we know we can get tertiary carbocations real easily, right? We protonate that alcohol. So let's just pick on this one. And anytime you see an alcohol in the presence of a strong acid, the first thing that you're going to do is protonate that alcohol, almost without exception. Okay? Nate, help me push the electrons here. and we end up with our protonated alcohol. Now, Delaney, explain to me again why this can't just come in now and displace the water as a leaving group.
Because it's got a bulky backside, so it doesn't attach to the back.
That's right, very good. So SN2 chemistry is shut down here, right? I've got a good leaving group. I don't have a good nucleophile, but my carbon group here is bulky. So all of this seems to suggest SN1 chemistry, right? All right. So now what happens? What happens, Maggie? Can't do SN2 chemistry, so what do I have to do? I have to do SN1. I could do E chemistry is not out of the question, but we're just talking about substitutions here. So how am I going to get my carbocation, Maggie? What has to leave? What leaving group? How do I do that? What arrow do I draw?
You draw one from the carbon bond it's connected to
Okay, this one.
up to the plus one.
Okay, very good. And so I end up with a tertiary carbocation plus water plus chloride, right? Now, if water attacks my carbocation, I just go back to my starting material. That's why it's in equilibrium, right? And if that happens, the reaction, I can't really tell that the reaction ever occurred, right? But every now and then, chloride will simply react with the carbocation, right? So, Paige, how do I draw that arrow? How do I draw the arrow from the chloride to the carbocation? From here to here? The other way. Very good. So I want the arrowhead going from the chloride to the carbocation, right? And when that happens, we get the tert-butyl halide. And why do I draw it only as this, a single arrow, and I don't draw the reverse here? It does go to completion, but why? That's right. Why can't I? Well, but I can. I can go back to a carbocation, but why do I draw it as that reaction? It does go to completion, that's right, but why? Whose law or whose principle? Le Chatelier's, yeah, the favorite guy that I pick on, right? Why does Le Chatelier's principle dictate that this happens? Because this is no longer soluble in water. It removes itself from the reaction mixture, and that's why we draw this arrow as going completely in this direction. Okay? Yes, technically there's a little bit of a reverse, but it lies so far to the, well, this is to the left in this case, as I've got it drawn, that the reaction goes to completion. Okay? So that explains why tertiary is faster than secondary. Okay? But why is methyl alcohol a faster reaction with HX than is a primary alcohol? Let's think about it. Why would, if Rose came into the lab and she took ethanol and she reacted it with HBr and she got the primary alkyl bromide, and Sam came in at the same time and said, I want to go to lunch faster, so I'm going to use methanol and HBr, and I told both of them, you can't leave for lunch until your reactions are done. Why would Sam get to leave and go to lunch or quicker than Rose? SN1 chemistry?
SN2.
Very good. They both do SN2 chemistry, and we know that because that's right. They don't form carbocations, right? Okay, very good. So why is it that, oops, that's a 3, excuse me. That's the intermediate we get, right? Why is this slower than this? This step is obviously faster than this step. Why is that? You got it. This has no other R groups attached to it. It is sterically unhindered. The bromide can come in from the back. All it's got to do is deal with those little tiny hydrogen atoms, kick the leaving group out. This bromide comes in from the back side here. Yeah, there's two small hydrogens, but there's also a pretty good size methyl group there. It gets in the way a little bit. They will both do SN2 chemistry, but this is more hindered than this one. And that's why you see that reversal of right there at the primary and methyls in this series. Okay? So as I mentioned, we can do the reaction of tert-butyl alcohol and concentrated HCl. It's one of the easiest things in the world. The mechanism is pretty straightforward. Okay? Brianna, how would I push the arrows in this first fast step? So this is my tert-butyl alcohol and my concentrated HCl. I'm just showing the hydronium ion here in this part of the mechanism. How would I draw the arrows in that particular step, the mechanism arrows? What's my Lewis base and what's my Lewis acid? Where would I start? Okay, on the alcohol, right? To a hydrogen, right? We're going to protonate it. That's exactly right. So this is going to function then as my Lewis base. This obviously is a Lewis acid, right? And so now we protonate. We get a new Lewis acid, Lewis base pair, right? The equilibrium lies to the right? Now, what happens in the second step? We lose our leaving group, right? And this is our slow step. We end up getting a tertiary carbocation. Why is that the slow step? That's true. But why is that the slow step? Water's a pretty good leaving group. Pardon? I've got to break a bond, and all bond breaking events are endothermic or exothermic? Endothermic. So I'm starting here, and I'm going to a carbocation intermediate, and the mountain that it has to climb is pretty tall or pretty small, relatively speaking? It's pretty tall. That's right. Because we're going from a system, right, that everything here has a carbocation, or excuse me, everything here has an octet, right, to the carbocation, which has a, does it have an octet? No, it does not. So it's high in energy, right? And so we end up with the carbocation, and now in the second, or excuse me, the last step, the chloride is going to function as what? The nucleophile or the electrophile? The nucleophile. And so we start from the nucleophile, we push the arrow, and we get the reaction, we get the tert-butyl chloride. Now this is obviously showing it as a reversible reaction, and technically that's true, but I would have just drawn that arrow because I know that this separates out as its own phase. Le Chatelier's principle drives that to the right, as we have it drawn here, and we can make this reaction go to completion, no problem. It's an SN1 mechanism. Okay. Now it turns out that you're almost always going to have a competition in these SN1 reactions with also an what? E1. E1, SN1 always compete with each other. That's always the way it works. So if we took tert-butyl alcohol and we mixed it with H3O+, a strong acid, again, we would protonate the alcohol. We would get a carbocation intermediate, just like we did before. Okay? But now we have a couple of pathways. If we have something that doesn't function as a very good nucleophile, it will remove a proton, and we end up with an elimination mechanism giving us an alkene, which in this case, is the alkene soluble in water or not? It is not, right? It does not satisfy our rules for solubility. It's a gas and it bubbles out of solution. Okay? If, however, we have a reasonably good nucleophile, we get substitution chemistry to occur. Okay? So it's very, very important to know what we have around in terms of our acid. We can't just use any old generic acid and get the product that we want. If we want this product, we need to use HCl. We need that acid to have, as its conjugate base, a decent nucleophile. Okay? So we could use HCl to get this. If we want a bromide, we could use HBr. If we want to get an iodide there, we can use HI. If, however, we want to do the elimination pathway, let's say Russell wants to make this alkene in his lab. He's not going to use HCl, HBr, or HI because he knows those will give him the substitution products. So he needs to pick what we call a dehydrating acid. Okay? Things that are strong acids but don't have good nucleophiles associated with them as their conjugate bases. Those are things like sulfuric acid. Sulfuric acid by itself is a dehydrating acid because HSO4- is a horrible nucleophile. So it will dehydrate the alcohol and give us the alkene. What other strong acids do we know of that are also known as dehydrating acids? Sulfuric acid is the go-to. Concentrated phosphoric acid is another one. And paratoluene sulfonic acid is another one, which is basically organic sulfuric acid. Okay? Those three acids, there are others, but those three acids are what you need to keep in mind when you're thinking about dehydrating an alcohol to an alkene. What other thing did we talk about last semester that would help ensure that we're going to do the elimination? Higher temperatures. That's exactly right. What other factor could we use to ensure that we get more of the substitution? Lower temperatures. That's exactly right. That's why we can take this alcohol, mix it with concentrated HCl at room temperature, and essentially get 100% yield of this and very little of the elimination, because we're using an acid that has a good nucleophile as its, relatively speaking, a good nucleophile as its conjugate base, and we're doing it at low temperature, and that all favors the substitution pathway, not the elimination pathway. Okay. Any questions about that? Brian?
So to do the elimination, you need a base and dehydrating?
No, there's no base involved here, really. The base is the counterion of the acid, which in this case, it's not a good nucleophile, so it will function as the base and abstract the proton. So do we need to go through that mechanism? Anybody want to see the mechanism? Sure? All right. Well, let's look at it. So Brian comes in, he takes his tert-butyl alcohol. Great job, Brian. He mixes it with sulfuric acid. And the easy way to think of sulfuric acid mechanistically is how? H plus and HSO4 minus, right? So I almost always above it just draw it as H plus and HSO4 minus. It's a complete lie, but it works pretty well, okay? Now, Brian, the alcohol is going to function as a Lewis base, and it's going to become protonated, right? All right. Now what happens? Mm-hmm. And we get our carbocation. And I told you that HSO4 minus is a horrible nucleophile, right? So we're not going to get any substitution product here. So now we're going to get elimination. How do I draw that? I've got 9 hydrogens that are all equivalent, right? So does it matter which one I go after? So Zaitsev's rule doesn't come into play, right? Or Hoffman's rule. Neither one. So what do? I simply draw one of the hydrogens, and what happens? get the alkene, plus I get my sulfuric acid back. So this dehydration reaction is what with respect to acid? It is catalytic. That's exactly right. Now, if we heat this reaction up, this reaction will go to completion. This reverse arrow here will be eliminated because this is a gas. It will blow out of the reaction mixture, right? And I can convert all my tert-butanol into isobutylene pretty easily. Whoop. I might have damaged it. I'm sorry. So let's look at the reaction of methanol and concentrated HBr. And we know in this particular case we're going to go through an SN2 mechanism, right? Why is that, Sam? Why must this go through an SN2 mechanism? It has no steric hindrance. That's one part. And what else? Well, it's not primary because it doesn't have another carbon, but it's unsubstituted. So if I generate a carbocation, it would be a methyl carbocation, right? Which has no substituents on it, which means it would be extraordinarily unstable, right? So we're not going to make it, right? We know that that's not going to be the route. So SN2 is the only feasible mechanism here, okay? And again, the first step is always the same. The alcohol plus the strong acid protonates the alcohol. Like I said, always, if you have an alcohol and a strong acid around, protonate it. That's your first step. And it's reversible, okay? Now we've got a good leaving group, but not good enough to give us a methyl carbocation, so we know we're not going to do that, right? So now in the second step, the bromide from the HBr, is that a better or a worse nucleophile than chloride? Yeah, it's a lot better, actually. And so now we're going to do the SN2 reaction. So Jamie Lube, show me how to draw the arrows. We'll draw that.
And at the same time.
At the same time, very good.
The bromide ion goes from the back side to that part.
That's right. And so we end up with those arrows like that, right? That's an SN2 reaction. We end up with bromomethane and water. And notice, again, we're not using a reverse arrow. And why is that? Le Chatelier's principle, right? Does anybody know what the physical state of methyl bromide is at room temperature? Solid, liquid, or a gas? It is a gas. Methyl bromide, you could do a little looking on it, has actually been used as a fumigant to kill a variety of pests. And the way that they actually generate it is through sulfuric acid and sodium bromide and methanol. So you can generate this on site, and you can make the gas that then is a fumigant. Do we use it as a fumigant in the United States? No, we do not. We do not. It's actually believed to create problems with the ozone layer. It is a very powerful fumigant. It's an alkylating agent. Does anybody know what I mean by that in the context of biology? Have you all ever talked about alkylating agents in cancer? Turns out that your DNA has a lot of nucleophiles on it. And methyl bromide's a pretty darn good alkylating agent, meaning it will donate its methyl group through SN2 chemistry. If you alkylate DNA, that's a good sign that you're going to give something cancer, okay? And it turns out that you're basically killing your bugs by alkylating their DNA. That's the easy explanation, okay? It's quite toxic, okay? All right, we find that the reaction of alcohols with the hydrogen halides, HCl, HBr, HI, we notice that the reactivity goes towards HI, HI being the quickest. So if Rose came into the lab with the same alcohol in 3 separate flasks and she put HCl in one, HBr in the other, and HI in the last one, that last one would be done first, then the HBr, and then it would, after some time, the HCl would be done. Okay, and it turns out that as we move in this direction, this is the stronger acid. Okay, which means it also has the weaker conjugate base. Okay, but what else do we have as we go from left to right here, which is basically going down the periodic table? What happens to the size of the halide? It gets bigger, and it turns out that iodide is more polarizable, which means it's more nucleophilic, even though it's larger. Okay? Chloride is smaller, it holds onto its electrons tighter, and it's a poor nucleophile. It's not a bad nucleophile by any stretch of the imagination, but in that series, it is the weakest nucleophile. And with primary alcohols, it turns out that it's such a weak nucleophile that the reaction is really slow. So we have to add an additional Lewis acid, zinc chloride, and like I mentioned earlier, zinc chloride plus concentrated HCl is known as Lucas's reagent. Okay? You can do some looking up on why that was developed in the early 1900s. So it turns out that the alcohol will react with the zinc. Zinc is very oxophilic. You all have probably heard of zinc oxide, right? What do you all use zinc oxide for? It's in sunscreen, yeah, and it's very stable. The zinc-oxygen bond is very stable, and that's why this works so well. So the zinc chloride will react with the oxygen atom of the alcohol to form this adduct, as we call it, which is a Lewis acid, Lewis base complex. And you have this now strong zinc-oxygen bond, which makes this a much better leaving group, okay, because you're getting that strength of that zinc-oxygen bond. And so now chloride can come in and efficiently remove, or displace, I should say, the leaving group and give us the product that we have through an SN2 reaction. The zinc chloride facilitates the rate of the reaction, but is it a catalyst? Catalysts lower the activation energy, right, of a reaction and speed them up. And that's exactly what's happening here, but is the zinc chloride a catalyst? I don't get it back. That's right. It's consumed. And catalysts don't get consumed in the reaction, right? This actually gives the reaction an alternative pathway, but it also consumes the zinc chloride as the leaving group. And so technically it is not a catalyst. Some people will say it is catalyzed by. Actually, it is promoted by, which is a different definition. Okay? So let's do some concept work here. I want you all to get together real quick and answer these three questions. What are the products going to be from these three reactions? How about that first one? What are we going to make? We're going to convert an alcohol into what? A bromide. That's the functional group transformation, right? We're going to convert an alkyl, or excuse me, an alcohol into an alkyl bromide. I know we're going to get a bromide because I'm dealing with HBr. Is this going to be an SN1 or an SN2 reaction? It's going to be an SN2 reaction. And so, how would I name the product? 1-bromopropane, that's right. Okay, or what? Propylbromide would be an acceptable name as well. How about the second one? This could be SN1. Could also be SN2, because secondary can do both, right? Could we tell here if it's SN1 or SN2 by the product? Why couldn't we? Same product either way, that's right. We have no chiral center to look at, right? Because this isn't a chiral center. So we can't really tell if it's going through an SN1 or an SN2 reaction. We'd have to do some additional experiments, right? But we're going to end up with chloropropane. What experiment might we do to determine whether or not Brian's reaction here goes by an SN1 or an SN2 reaction? What might he measure? Obviously, we can't look at chirality because it's not a chiral compound. Well, but that would be if it's chiral. We don't have that, right? Okay, we could look at solvents. We could look at that. That's true. What else could we do? Reaction rates. That's exactly right. So how would you set that experiment up, Rose? And which one would you change? If I change the concentration of alcohol and I see a direct relationship to the rate of the reaction, that's equally true for SN1 and SN2, right? I'd change the concentration of the HCl and the zinc chloride, right? And if I see no dependence on the HCl concentration with the reaction rate, then I know it must be an SN1. And if I saw a dependence, SN2. And if I saw something in between, it may be going through both, right? Which is possible here. How about the last one? It's going to be SN1. And why do you say that? All right, so I got a tertiary alcohol. How many products am I going to get? I'm going to get 2. That's exactly right. I'm going to get one where the chloride is axial or equatorial, and one where it is equatorial. And given the size of chlorine and a carbon atom, given that they're not too far apart from one another, what would you predict the ratio here to be? Yeah, it's going to be a lot of one and a lot of the other. I mean, I don't know that it'd be 50-50, but it's going to be substantial in both cases, okay? All right, so here's what's going to happen. We're on the last couple minutes here. Monday we have an inverted lecture. I'm not going to be here, okay? So my graduate student's going to come in. There are pen casts on this stuff from PBR3 and SOCl2 already in Blackboard. So go to the Chapter 11 folder. There is a couple of pen casts there. Watch those pen casts. I will put on YouTube the stuff from Wednesday and the stuff from today. That'll be on my YouTube channel, okay? So I know there's a couple of new people in here. I'll send out the link again to my YouTube channel so you have it, and you can watch and do whatever you need. Have a good weekend, everybody.